Have you ever, wanted to run a different operating system on your computer, but without actually installing it and messing up your main setup?
Right. Or maybe you needed a virtual lab, like for testing,
Hmm.
or you've got some ancient software that only runs on, I don't know, Windows XP or an old Linux kernel.
Exactly. Or maybe you're on the other side, dealing with cloud stuff, managing huge server farms.
Uh-huh. Where carving up one big physical machine into lots of smaller, isolated virtual ones is just essential. It's how everything works.
Well, all of that flexibility, that ability to run multiple totally separate operating systems on just one physical computer,
Yeah.
it all hinges on this core technology. It's called a hypervisor.
Yeah, hypervisor. Or sometimes you'll hear it called a VMM, a virtual machine monitor.
Yeah.
Or just, a virtualizer.
And that's our deep dive for today, hypervisors. What are they really? How do they actually manage this? And where did the idea even come from? Because the history is surprisingly old.
Yeah, it goes way back.
And why are they so fundamental now? I mean, from huge data centers, maybe even down to the phone in your pocket.
So our guide for this is a really comprehensive look at the Wikipedia article on hypervisors.
Hmm.
We're going to dig into the key ideas, the history, the impact, all based on that source.
Okay, let's get into it. At its core, what is a hypervisor actually doing?
Fundamentally, it's a layer. It can be software or firmware, sometimes even hardware features help out. And its job is to create and run virtual machines, VMs.
Right, VMs.
So think of your physical computer, that's the host machine. The hypervisor runs on that host.
Yeah.
And then it lets you create and manage one or more guest machines. And each guest machine runs its own complete operating system, could be Linux, Windows, macOS, whatever.
So it kind of sits in between the actual metal, the hardware, and the operating systems running inside those virtual bubbles.
Exactly. It presents this virtual platform to each guest OS. It tricks the guest into thinking it has its own CPU, its own memory, storage, network cards.
Mhm.
But really, the hypervisor is the puppet master, managing the real physical resources underneath.
And this is the clever bit, isn't it? It's not like an emulator that has to pretend to be a different kind of computer chip, which can be slow.
That's a super important distinction the source makes. For performance, the key is that the guest OS inside the VM runs most of its instructions directly on the host machine's actual CPU, like native speed.
Ah, okay.
The hypervisor only has to jump in for certain things, what are called privileged instructions. Things the OS would normally do to talk directly to hardware, like messing with memory pages or starting I/O operations. The hypervisor catches those and handles them safely on the guest's behalf.
Gotcha. So that direct hardware execution is why VMs can feel pretty fast. And this setup lets you do some amazing things, right? Like one physical server running, I don't know, tens of different OS instances, all nicely separated.
Totally. Each guest OS is walled off from the others. If one VM crashes or gets hacked, it generally doesn't take down the others or the host system itself.
That's huge.
And it's a really different model from, say, containers, which is also virtualization, but at the OS level.
Right, like Docker.
Yeah. Containers all share the same host operating system kernel. They isolate applications and processes, but not the whole OS. Hypervisors give you a full, independent machine virtualization, separate kernel, separate everything for each guest.
That's a really clear distinction. Virtual machine versus virtual environment on top of an OS. Okay, the name? Hypervisor. It sounds like it's supervising something that's already supervising.
And that's exactly it. The source mentions the term goes back to maybe 1970 or so.
Wow.
Yeah. So traditionally, the core of the operating system, the kernel, is called the supervisor, right? Because it supervises everything else. Hyper has just used like a stronger version of super. So the hypervisor is literally the supervisor of the supervisors. It manages the operating systems. It's actually a pretty descriptive name when you break it down.
It really is. Makes you think about those layers. The source also mentions a subtle difference sometimes made between hypervisor and VMM.
Yeah, you sometimes see this, especially in more technical discussions or maybe around microkernels. The term hypervisor might specifically mean the really low-level stuff, the kernel code or hardware features that do the core virtualization work, like trapping instructions, handling memory virtualization.
Okay, the engine bit?
Kind of, yeah. And then VMM, the virtual machine monitor, might refer to the higher level part, often running in user space, that uses that hypervisor engine to actually manage the VMs, loading the guest OS, setting up virtual devices, maybe the user interface.
So it's more about how you architect the system internally.
Pretty much. It's splitting the job into layers. but often people just use hypervisor to mean the whole system, and that's usually fine.
Okay, got it. Now, how are these things actually built or structured? The source talks about a classic way to classify them from the early 70s.
It does. Robert Goldberg's thesis in 73, he came up with the Type 1 and Type 2 classification, which is still widely used.
Let's start with type 1, the bare metal ones.
Right. Type 1 hypervisors run directly on the host computer's hardware. There's no regular operating system underneath them. They are the first layer of software. They control the hardware directly, and then they load and manage the guest operating systems on top.
So bare metal, because they're right on the hardware.
Exactly. And those very first IBM hypervisors back in the 60s, they were this native Type 1 style. Modern examples the source gives are things like Microsoft's Hyper-V, ES, VMware, ESXi, stuff you run data centers on.
Okay. And type 2, that sounds more like something I might run on my laptop.
Probably, yeah. Type 2 hypervisors run on top of a normal operating system like Windows, Mac OS, or Linux. They install and run just like any other application.
Ah.
The VMM software itself is a process running on your host OS. It still creates that isolated virtual environment for the guest, but it relies on the host OS for things like device drivers and scheduling. Examples the source gives are VirtualBox, VMware Workstation, Parallels Desktop.
The difference seems pretty clear then. One is the base layer, the other runs on the base layer. But you mentioned the source says the lines can get a bit fuzzy.
It can. It points to things like KVM in Linux or Bive in FreeBSD. These are actually kernel modules that get loaded into the standard host OS. But these modules add the core virtualization functions to the host kernel, essentially turning the host OS itself into something that can act like a Type 1 hypervisor for managing guests directly. So while it's part of a conventional OS, it enables that more direct, bare metal-like management.
Interesting. So the implementation can blend the approaches, but the core idea holds directly on hardware, Type 1, versus on top of an OS Type 2.
Yep.
Okay, let's rewind. You mentioned IBM in the 60s. This tech is way older than, the modern cloud era.
Oh, absolutely. The history is fascinating. The source takes us right back to the 1960s, IBM. The first hypervisors really designed for what we call full virtualization, letting multiple independent OACs run came out of there. Systems like Simon, which was a test tool, and CP40, which was the first version of CPCMS. These were running around 1967.
And the big deal wasn't just running multiple programs, but actually virtualizing the operating system's special powers.
Precisely. Before that, systems could multitask applications, sure, but they all shared one OS kernel, one privileged state. CP40 was designed to actually virtualize the hardware supervisor state. That was the breakthrough. It meant you could run multiple entire operating systems, each thinking it owned the machine, all on one box.
What made that possible back then? What was the enabling tech?
Two key things, really. Dynamic address translation mapping the memory addresses the guest OS thinks it's using to the actual physical memory addresses. And second, the ability to trap and handle those special privileged instructions we talked about, the ones the OS uses to control the hardware. The IBM System 360 Model 67 from 1966 was actually designed with hardware features like page translation tables specifically to help make this full virtualization work efficiently.
So why bother? Why were they doing this in the 60s? What problems did it solve for them?
And this is where it gets really interesting. The problems were surprisingly modern. The source highlights two main drivers. First, making systems more robust, more stable. If one OS and its virtual machine crashed, the others kept running. On a critical mainframe, that's a big deal.
Yeah, definitely.
And second, maybe even more importantly for development, it let them test experimental OS versions or even simulate new hardware designs without needing extra expensive physical machines and without risking the main production system. They could spin up a test environment safely.
Wow. So the basic reasons: isolation for stability and flexible test dev environments. They're exactly the same reasons we use virtualization in cloud today. They were solving 1960s mainframe cloud problems.
It's uncanny, right? The tech evolved. IBM System 370 came along in the 70s, and VM370, which was IBM's official version of CPCMS, brought virtualization to a wider audience around 1972.
And VM literally meant virtual machine, underlining that full virtualization idea.
Correct. VM370 virtualized everything the guest OS saw. The source mentions that CPCMS and VM actually had this really active user community, almost like an early open source scene, sharing code and improvements. But, well, internal IBM politics meant that VM kind of lost out to big batch systems like MVS for a while. It became more niche.
But it didn't disappear. It came back.
Oh, yeah, big time. Around the year 2000, ZVM, the modern version, saw a huge resurgence, especially as the go-to platform for running Linux on IBM's Big Z mainframes. It was perfect for consolidating hundreds or thousands of Linux servers onto one reliable mainframe.
That's quite a journey. The source mentioned something really specific about how VM handled certain operations quickly, like a shortcut.
Ah, yes, the DIAE instruction. This is pretty clever. Instead of using the normal way an OS asks for system services, which had to be fully virtualized and could add overhead, the VM control program used a specific hardware instruction called diagnose, or DIAE. It wasn't typically used by normal programs, so the hypervisor could intercept it when a guest OS issued it.
Okay.
It basically became a special, fast communication channel directly between the guest OS and the hypervisor for certain requests, like maybe accessing files efficiently, bypassing the more complex virtualization path for standard OS calls. It shows the kind of engineering needed before hardware explicitly supported this stuff.
That's really ingenious. IBM also did LPRs later, logical partitions.
Yep, in 1985, they introduced PRSM, another hypervisor approach focused on creating these hardware-enforced logical partitions, or LPARs, on their mainframes, another way to slice up the machine.
Okay, so hypervisors have this really deep mainframe history. But the massive scale we see now, running the internet, the cloud, that's more recent.
It really is. The source points to roughly 2005 as when things really took off again, especially on standard Unix, Linux, and eventually x86 servers. Several factors just came together.
What were the big drivers this time around?
Well, first, the hardware just got ridiculously powerful. Multi-core CPUs, tons of RAM, way more than one OS instance often needed for its workload.
Right, machines were sitting idle a lot of the time.
Exactly. Which led to the idea of server consolidation. Take dozens, maybe hundreds of underused physical servers and squash their workloads onto just a few much bigger machines running lots of VMs.
That saves a ton of money, power, space.
Absolutely. Huge economic and management benefits. Suddenly, managing massive server farms, render farms, the beginnings of cloud infrastructure, it got way easier. You could manage virtual resources with software, not by physically touching thousands of boxes.
Makes sense.
Plus, you got better security through isolation again, easier deployment for apps needing specific setups, and you could over-provision, kind of promise more resources to VMs than you physically have, betting they won't all peak at once. Very efficient.
Now, before x86 really dominated the server room, other big Unix players were already doing this on their own hardware, weren't they?
They were. The source makes that point. Companies like HP, IBM, SGI, Sun, they had virtualization tech well before 2000, mainly on their big, expensive systems, but sometimes on mid-range ones, too.
Can you give us a flavor of what those looked like based on the source?
Sure. Sun, which became Oracle, had logical domains, or LDOMs, on their Spark servers. They could run multiple copies of Solaris, Linux, FreeBSD. Spark's architecture was apparently pretty well suited for virtualization early on. HPE had Integrity virtual machines for their Itanium-based systems, could host HPUX, Linux, Windows, even OpenVMS. IBM's Power Systems used the Power Hypervisor, or PHYP. That's firmware-based, Type 1, bare metal stuff, creating those logical partitions, LPRs. Power Systems are known for being able to dynamically shift resources around between LPRs and for really high reliability features built into the hypervisor layer.
So yeah, established tech on the big iron.
Yeah.
But it just exploded when it hit the commodity x86 servers.
Totally. Same motivations, just applied to the volume market. Early attempts at x86 virtualization back in the 90s often relied on pure software emulation, like the Box project. That was slow, functional, but slow.
Right. Not practical for real workloads.
Not really. The game changer for fast, efficient x86 virtualization came a bit later.
And that's when Intel and AMD stepped up with hardware features.
Exactly. The source flags 2005 as the key year here, with Intel introducing VTX and AMD bringing out AMD-V. These were extensions built right into the CPUs specifically to help hypervisors.
What do they do?
They provided hardware support for the tricky parts, like trapping those privileged instructions automatically and managing the virtual memory mappings much more efficiently. It took a huge burden off the hypervisor software and made full virtualization on x86 really fly.
Before that hardware help was common, though, there was another approach they used: paravirtualization.
Yes, paravirtualization, or PV. It was a really clever workaround, especially on x86, before VTX and AMDV were mature or ubiquitous. The idea is, instead of trying to fool a totally standard OS, you modify the guest operating system.
Modify the guest.
How? You make the guest OS aware that it's running inside a virtual machine. So instead of just executing a privileged instruction and waiting for the hypervisor to catch it, which takes time, the modified guest OS makes an explicit call, a hypercall, directly to the hypervisor saying, hey, I need you to do this privileged thing for me.
Ah, so it cooperates.
Exactly. The source mentions Exen was a big proponent of this early on. Parallels had a similar idea with their hypercall. Even IBM VM's diagnose code could be seen as a form of this cooperative paravirtualization. It cut out a lot of the overhead when hardware assist wasn't good enough.
Makes perfect sense. Modify the guest to be VM-friendly for better speed. Okay, we've covered mainframes, servers, desktops. What about the really small stuff? Embedded systems. Is virtualization a thing there too?
It is, but it's a different world with different needs. Think cars, industrial controllers, network routers. Here the priorities are often things like extreme reliability, security, real-time responsiveness, fitting into tight memory, low power draw. Less about raw server consolidation.
And the hardware is different too, right? Not just by 86.
Much more diverse. Lots of ARMM, MAPS, PowerPC, though some by 86 too. For virtualization to work, you still need basic hardware support, like a memory management unit, MMU, and different CPU privilege levels.
So how do hypervisors fit in there?
Increasingly important. And interestingly, because the manufacturers often build the hardware and control the embedded OS source code, paravirtualization is often quite popular. They can modify the guest OS easily to optimize for performance and real-time behavior.
But full virtualization, running unmodified OCs, is that happening too?
It's growing, yeah. The source notes that newer chip designs, especially ARMv8 with its dedicated EL2 hypervisor mode and some high-end MI cores, are now offering hardware support for full virtualization as an option, so it's becoming more feasible.
What other unique demands do embedded hypervisors face?
Things like really efficient sharing of resources because they're often constrained.
Yeah.
Also, very fast, low latency communication between different VMs on the same chip. Imagine in a car, the infotainment system in one VM needs to talk to the driver assistance system in another VM very quickly and reliably.
Okay, yeah.
And also things like managing power across all the VMs globally, coordinating scheduling for real-time tasks, and having really strict controls over how information can flow between isolated VMs for security reasons.
It's really amazing how this one core idea adapts from massive mainframes decades ago to tiny chips and devices today, but with great power, especially the power to sit underneath the main operating system. There's got to be a dark side, right? Security risks.
Absolutely. And the source brings up a really significant one. Hyperjacking?
Hyperjacking. That sounds like hijacking the hypervisor itself.
Pretty much, or rather, malware installing itself as a hypervisor. The idea is malicious code could potentially insert itself underneath your actual legitimate operating system.
Whoa. And why is that so bad?
Because it's running at a deeper, more privileged level than the OS itself. Think about your security software, your antivirus, your anti-malware tools. They run on top of the operating system.
Right.
If the malware is running below the OS, it could potentially intercept anything, your keystrokes, network traffic, what the OS tries to do without the security software even knowing it's there. It's like being bugged from underneath the floorboards. It completely breaks the trust model.
That is, yeah, that's a scary thought. Has this actually happened? Are there real examples?
The source mentions some research projects that demonstrated the concept, like the Subvert rootkit from Microsoft Research and the University of Michigan folks, and also the blue pill malware concept was talked about. These were proofs of concept or theoretical attacks.
So maybe not widespread in the wild.
It's hard to say definitively if it's widespread, but the source does note that claims about these things being completely undetectable have been challenged by other security researchers. It's a complex cat and mouse game. Detecting things operating at that level is really hard, but not necessarily impossible.
And people are working on defenses.
Definitely. It's an active area. The source mentions research like the HookSafe tool, also from Microsoft and NC State researchers, which aims to run at the hypervisor layer, specifically to protect the OS kernel above it from being tampered with by rootkits. So using the hypervisor for defense.
Wow. What a journey. From solving 1960s mainframe efficiency problems through a quieter period and then exploding to power the cloud and modern IT, finding uses in embedded systems, and now presenting these really fundamental security challenges.
It really is a technology that's gone from being almost an academic curiosity or a big iron specialty to just underpinning so much of modern computing. It's often invisible infrastructure, but it's everywhere.
And for you, the listener, chances are you're interacting with hypervisor-powered systems constantly. Every time you visit a major website, use a cloud service, run enterprise software, heck, maybe even parts of your car's electronics or your smart TV, it could all be running inside VMs managed by a hypervisor.
So maybe here's a final thought to chew on from this deep dive. We've established that hypervisors run underneath the operating systems we normally interact with. They manage everything. And we've seen there's at least a theoretical possibility they could hide malicious activity from everything running above them. Given how widespread and fundamental they are now, what does that imply about how much we can really trust the layers of software running on our machines, controlling our data, and delivering the services we depend on every single day?